want to go through some of the examples from chapter 17, some of the more complicated examples starting in question 21. In this example, it asks us specifically to talk about are the assumptions and conditions met? What is the mean and standard deviation in a situation like this? And then what would be a certain probability? So for question 21, now I'm recommending that if you haven't done the question, to go do the question first, and we can talk about the responses of the questions kind of here. Question 21 is about loans, and it gives us in the paragraph that it says 7% of all people who get loans don't repay them on time, and that they take a sample of 200. So you see those examples listed out here in the beginning. The first question is, what are the mean and standard deviation? Well, we know that the mean is just given to us. Now, in questions like this, when we're talking about sampling distributions, the mean of the distribution is always going to be given to you. The standard deviation, on the other hand, won't be. And this problem is very specific, that it's asking for proportions. Proportions are parts of the whole, right? Probabilities, percentages, things like that, not whole counts of people. So in this case, it really does want us to give an answer that looks something like this versus how many people out of the 200 this satisfies. So be careful of that. You wouldn't necessarily get the question wrong in this case, but there can be questions in the future that you can have some confusing situations happen up, and you start mixing units with percentages, mixed with counts, and you're going to get a lot of things incorrect. Next part of this asks what assumptions underlie the model and which ones have been met. So there are 4 that we look at: randomness, independence, 10%, and success or failure. Randomness is stated in the problem, so I just need to mention that it's stated. Independence, along with randomness, a lot of the times have kind of a common sense approach to them. They are considered assumptions, so it's not that I can prove it. I just need to make sure that it's logically reasonable to make this assumption. Independence means that loans are assigned independently to individuals, and that one person getting a loan doesn't affect another person getting a loan. And that makes sense. And so we can assume that the loans are assigned independently. 10% in success or failure are more like conditions that need to be checked with a little bit of math, right? Avoid all costs of putting little check marks beside all these things and not providing any sort of evidence to show that they are satisfied or not satisfied. With 10%, the way we do that is you're going to take that sample size times 10, and you're going to get a certain number. What we want to make sure is that the population is greater than that number. If that's true, then it passes, all right? If 2,000 in this case would be larger than the total number of loans given out, then I would say that it fails the 10% condition. We want to make sure that my sample size isn't more than 10% of the population. So for a sample of 200, the population has to be at least 2,000 or larger, and that definitely seems true here. For success or failure, it's more of a little math. 200 times, or n times p and n times q, the probability of failure and probability of success, right? P is 0.07 and q is 0.93. So when you multiply those through, you get 14 and 186. I need to see those numbers actually written down, and the fact that both of them are greater than 10 means that it passes the situation, which is why you see us do this normal model stuff. Okay, the last part of this asks about how much, or what's the probability that over 10% of our clients would basically not pay their loans on time. And so you're looking at it here where the curve is drawn like a normal model. I put the mean down at the bottom of 7%, and the mark that we're looking to start shading the area under the curve is at 10%. Now, if you did this with a number of people, and the number of people were all kind of carried through along with the standard deviation, then you're going to get the same answer that I'm going to get, right? I use normalcdf. We start at 10%. We go up to positive infinity, and the mean of 0.07 and the standard deviation of 0.018, right? That's where we got that up here. Now, if you multiplied the 10%, the 7%, and the 1.8% by the sample size of 200, and you replaced each one of these with the total number of people involved, then proportionally, you're going to get the exact same probability that I would have gotten. You just don't want to mix these percentages here with a certain number of people, like counts. That means your units aren't matching, and you'll get the wrong answer. Usually, if I get a 1 or a 0 in terms of probability, I'm going to think I've messed up. I'm going to go back and I'm going to double check to make sure I get it right. So you end up getting about 4.8% or 0.048 is the probability that more than 10% of people who get loans wouldn't pay them back. Question 23, this goes back in and does a little bit of review about normal models. It's kind of in the same light, but it's using 68, 95, 99.7 rule. And the way this sets up is in order for me to use the normal model, I have to make sure that that actually follows a normal model. So we can kind of look at it, we can check that particular condition, which is the success or failure condition. Here you get 296 and 104 when you multiply them together, which obviously both of those are greater than 10, so we can definitely assume this is approximately normal. Now, the center is still at 74%. They tell you that in the paragraph. And then go ahead and recalculate my standard deviation according to a sample of 400. And so you're going to do 0.74 times 0.26. That's P times Q divided by N. And this gives me the proportion for the standard deviation. All right, so I take that standard deviation and I add that 3 times and I subtract it 3 times. And I get the x-axis here labeled with the percentage of students that would return to their same school they were at as a freshman for their sophomore year. Some things you can write about this would be 68% of all samples would generate an average that would fall in between 71.8% and 76.2% for the percentage of returning freshmen for their sophomore year. I could say 95% of the samples would generate averages between 69.6 and 78.4% would return as sophomores to the same school, and so forth. You could write that for all 3 of those numbers. Question 25 kind of takes this into the next step. 2 things here to note that you might not have written down. We calculate p hat. Remember, the hat indicates it's an estimate. This is my statistic, right? We're told that the sample, you had 522 freshmen returning with a 603 total sample size. So if I divide that by that, I get that's about 86.6%. Compare that to 74% what I was expecting to have in terms of average results. Would we say that this is enough for a school to have bragging rights? Or I guess you could translate that into, is this an unusually high percentage? We know that every school is going to have slightly different numbers, so getting percentages to be around 74, give or take a little bit, is normal, is what's expected. But we don't know the standard deviation necessarily, so I'm not sure if 86% is really high or it's just kind of on the high end of what we would expect. One of the ways you can test for unusual observations is with z-scores. Now, we've already determined that this was normal back in question 23, so when we increase the sample size, I would just assume that it's going to be even more normal than it was before. So we went ahead and we used the z-score for this chapter. This is p hat minus p divided by the standard deviation. So statistic minus parameter divided by the standard deviation formula that we're currently using for categorical data. Now, when I do that, I'll plug all that stuff in and I get 7.05. So in other words, 86.6% is over 7 standard deviations above the mean. We defined a long time ago that over 2 standard deviations away from the mean would indicate unusual observations. So in other words, if I were to randomly select a school from this situation, what's the chance that I could get a school that had a retention rate as high as 86.6%? The probability of this occurring is basically 0. I shouldn't be able to randomly choose a school like this because this school is exceptionally large retention rate. It doesn't follow what most schools would do. So with that respect, they do have bragging rights. This is a very unusually high observation. Question 44, this is a great question. If you haven't done this one, I would encourage you to go through that. We did this one in 5th period today because we had the extra time. This is a lot like question 54, which everyone did, but this is just another chance for you to kind of make sure that you understand the differences between sampling distributions and just a traditional sample. So let's look at part A. Here we're talking about rainfall averages in Cornell, in New York. And what we're looking at here is it asks, what's the chance that in a particular year you have more than 40 inches of rain? All right, it's a single sample of 1 from a population, so this is just a traditional normal CDF question. They told us it's normal in the problem, so I don't have to justify that in any other way. Not to mention, it's just 1, right? So it's a very small sample. I use normal CDF in the traditional sense. My mean is here, my value that we're working with is here. It gives me a standard deviation, and we're kind of going 40 and above. So we do that, kind of plug it in, 13.67% chance to get a year that has 40 or more inches of rain in it. Part B goes into inverse norm, kind of giving you a bit of review here. It says, what's the number that marks off the driest of all of 20% of the time of the rainfall? And so I'm looking for that number X that separates the bottom 20% from the top 80. So we would work with normal CD or inverse norm here. 20% is the area towards the left. I have 35.4 as my mean and 4.2 as my standard deviation. It says, well, if you had a rainfall that totaled about 31.87 inches or less, the 31.87 separates the bottom 20% from the top 80%. That's that X value. In part C, that's when it switches over to a sampling distribution. And you can determine that because it's talking about not a single number that's a certain rainfall, but an average amount of rainfall. Whenever you see mean amount or average results, then you are really getting into what we call a sampling distribution, which means this little formula we do with the standard deviation, this needs to happen. Everything else is going to stay relatively the same, but this changes into a sampling distribution. Now, we're already told that the population is normal, so that means the sampling distribution will also be normal. It's going to have a mean of 35.4. The standard deviation divided by the square root of the new sample size, which is 4, gives us a new standard deviation of 2.1. Right? The next part says, okay, so now that you have a sample of 4 years, what's the chance that the average of those 4 is less than 30? And so it's kind of going in here, taking what we found out for this situation and using normal CDF, but making sure I'm using that adjusted standard deviation because now we have a sample of 4 that we're looking to find the average result for. So using normal CDF, just like we've laid it out, and you get a very small percentage of 0.0051. So just slightly larger than 0.5% chance of having 4 years all average to have a really small amount, less than 30. So not very likely to happen. Okay, this is question 54. This is the one that we did at the end of class. Most every class did this, if not all. This is a lot like question 44 that just went through. This is about potato chip bags being underweight or overweight. Question part A asks just what percentage of bags are underweight. So they advertise a weight of 10 ounces. So under that amount would be what we would call underweight. And so I'm just using normal CDF in terms of this traditional sample. And we set it up like this, where we get that percentage and you get about 0.048% probability of having a bag be underweight. Part B, there's probably a number of ways that you could have done part B. For me, I was trying to think about what's the easiest way, what's the least amount of adjustments I would have to do. When I read part B, and I'll just read it now. Some of the chips are sold in bargain packs of 3. What's the probability that none of the 3 is underweight? This just reminded me of a binomial PDF question. What's the probability that you had, out of 3, you got 0 successes? And so I tended to do it the binomial PDF direction. So you had a sample of 3. Previously, we found out in question part A, or part A in this part, we got the probability of getting a bag that's underweight. So I used that probability here. And I wanted to find out 0 of them were actually underweight. So it turns out to give you 86.34% of the time, you would have 0 bags be underweight when you've chosen 3 out of the population. Here again, just like in question 44, it changes over to talking about sampling distributions. In this chapter, sampling distributions deal with average results, and you can see that start off talking about average results here. And I did this 2 different ways. The first way is the old way. This is what we did back in chapter 15, and you can definitely still do things like this. I just wanted to show you how it changes and how much less work we have to do in the new method versus the old method, but I also wanted to make sure that we understood how they connected to each other. Here, it's talking about getting 3 bags, and what would I expect to happen if I had chosen 3 bags, and what's the chance that those 3 bags would be underweight. In this case, if I had chosen 3 bags, they would bag plus bag plus bag, right? Then I would expect the average result of the sum of all 3 bags to be about 30.6 ounces. Or is it grams? Yeah, ounces. And so if I do the standard deviation, remember it's x plus x plus x. Be careful, we have to do 0.12 squared plus 0.12 squared plus 0.12 squared for the new standard deviation. When you do that, you can either multiply by 3 out here or just add them together 3 times to get your 0.2078 standard deviation. And now we're going to go back into normalcdf and kind of work it out like using the information we found here, which you get 0.0019, pretty small. Now, if I do the new method, rather than doing all the recalculations of averages and standard deviations, we can do it a little bit differently, which is a lot simpler. We know that the average bag is going to have 10.2 ounces. And we know that being underweight is 10 ounces for an average bag. So what I'd like to do is, rather than adjusting everything else, I'm just going to adjust the standard deviation down to the average bag. And so we take the original population standard deviation divided by the square root of the new sample size, and that's going to give me a new standard deviation, which is representative of the average bag, not the individual bag, because average results must have a much smaller standard deviation than before. So here, we can kind of plug that in just like we did. It's just like we were setting it up here. So this part of it, the curve and what we're looking at, doesn't change, but the standard deviation will change because we got a new, larger sample. Last time it was 1, now it's 3. We get the exact same thing again, 0.0019. The last part of this question, it's just kind of a follow-up of what we did before. The last part asks, what's the probability that the mean weight of 24 bags would be below 10 ounces? Well, last time it was 0.0019, so it's like less than 0.2% last time. So I'm expecting this one to be extraordinarily small. And we set it up here again. Curve looks the same. What does change is the standard deviation changes again. So 0.12 divided by the square root of 24, that's going to give us 0.02449. Remember, we started off with a standard deviation of 0.12, so 12%. Now we're down to less than 2.5%. So it's dropped considerably smaller than it was to start off with. So we set that up, and your calculator, I'm not rounding that to 0. That's what the calculator gives you back. I'm sure the calculator probably is rounding. This is probably quite a large number of standard deviations. Remember, anything past 3 is a big number. So it is basically 0 chances that you could get all 24 bags to be underweight, or at least averaging to be underweight. That's usually going to happen. Most of the bags are going to be the average weight. So getting all 24 of them to be underweight would be very, very unlikely to happen. If you guys have any questions about this, please feel free to reach out and let me know. And otherwise, we'll talk about it later. See you in class.